Now we are going to see the two sample confidence intervals using Python, and the first one over here would be the two sample pooled t interval. So let me just mention that two sample pooled t interval. So in this case, if you can recall, we have a random sample coming from normal distribution with parameters mu1 and sigma square, and there is another sample which is say y1, y2, ym, which is also coming from your normal distribution with mean mu2 and same variance, that is sigma square. So in this case, we have the common variance between the two populations. So let us see how do we work with this. So first of all, as we usually do, we will import numpy as np. Okay, we know that this is used for your numerical operations, and then from scipy.stats we will going to import t, because we are going to work with the t distribution. Okay, now let us set the random seed np.random seed. So you must have seen that this line, basically we have been using it when we started working with your random samples, right? Because we do not want this sample to be updated every time we run this code. In order to ensure that, we have given this value over here. You can give any non-negative number over here. So let us see what are the true population parameters. True population parameters. So in this case, my true, the first mu1, let it be 35, and true mu2 be 30. So mu1 and mu2 is given to us, and the common variance, that is true sigma squared, we are writing, because SQ suppose squared is 25. This is the common unknown variance. After this, we will also mention about the sample size. So first, let the size of the first sample be 40, and for the other one, let us denote by m, let it be 30. So these are the sample sizes. Now we are ready to generate a random sample for the two populations. So generate a random sample. In this case, we are going to define a variable data sample 1 as np.random.normal, because we have to draw a random sample from your normal distribution. Okay, so here it means that it is going to use your numpy libraries, this function, and we are going to draw a sample from normal distribution whose mu and sigma square is already defined, so I can mention that. So true mu1, and variance would be, because here we have used variance, so I can take the square root of np square root of true underscore sigma underscore sq, and finally the size of the sample would be n. Okay, so it will draw a sample of size 40 from normal distribution with mean 35 and variance 25, or you can say standard deviation 5. Similarly, I need to draw a sample from the second population also. So let me use data sample 2 for this. So I can use the same command. So np.random, so here it would be 2. Since variance is same, so this would remain the same over here. The sample size would be different in this case. Now we will set the confidence level. So conf level, let that be 0.95. Okay, and alpha will be basically 1 minus of confidence level, so 1 minus conf level, and we need the degrees of freedom, so let that be df be n plus m minus 2, right? Because if you can recall from the result that we discussed in the previous lecture, so in that we had the degrees of freedom would be n plus m minus 2 because it is following t distribution, and the critical value for t critical would be found using this percent point function, which we have defined earlier also, 1 minus alpha by 2. And so let me not use df over here because it is going to create, let me use dof, degree of freedom. So here df would be dof now we will calculate the sample statistics. So basically in this step what we have done is that we have first defined the confidence level and we have set it to 95%, and alpha will be 1 minus of confidence level, which is alpha is the significance level, right? So it is basically representing the probability of making your type 1 error. Degree of freedom is n plus m minus 2 because it is a 2 sample t test, and t critical we have found out using this is basically the critical t value based on the confidence level and the degrees of freedom, and we will use this to determine your margin of error for the confidence interval. So we will calculate the sample statistics now. So mean 1 would be calculated using np.mean, and here we would write for the first sample it will calculate, and in mean 2 we would store the mean for the second one, data underscore sample 2. Okay, similarly SD1 also can be calculated, that is standard deviation. For this again we will use numpy's std function. So here again we would write data underscore sample 1, and here we will also specify that it is calculating the sample variance and not the population variance by specifying this GDOF as 1, and standard deviation 2 would be here again, so here we will use 2. Now you are ready to calculate your pooled standard error. Calculate the pooled standard error. Pooled STD only I would write. So here we will write np.sqrt. basically we are looking at square root. So if you can recall, it is basically in the numerator we have n minus 1 times sample variance of the first one plus m minus 1 times sample variance of the second one, and the whole in the denominator we have n plus m minus 2, and if I take the square root of that, that will be your s suffix p, that is the pooled standard deviation or pooled standard error. np dot square root, so here I need to first write the numerator, so it is n minus 1 times SD1, we have used this notation, SD1 plus m minus 1 times SD2, and this whole is divided by the degrees of freedom, that is DOF, that is n plus m minus 2. So here there would be one more bracket. Okay, after this we can find out the margin of error. For margin of error we can just write MOE. So T critical into, we multiply it with the pooled one, that is pooled SD, and then we multiply it with 1 over n plus 1 over m, square root of that thing. So we will write n np.sqrt 1 over n plus 1 over m, right? Because if in this case 2 sample pool t interval, the confidence interval came out as sample mean x bar minus y bar plus minus t alpha by 2, that is t critical at n plus m minus 2 degrees of freedom, and then we multiplied it with this pooled standard deviation into SP into square root of 1 over n plus 1 over m. So pooled, it is pooled STD, not SD. Now, since you have calculated the margin of error, now you are ready to find out the confidence interval. Calculate the confidence interval for difference of means. When you are looking at difference of means, so first of all, let us write difference mean. Basically, it would be mean 1 minus mean 2, okay, because that we have already defined, and your CI would now be basically the difference of mean, that is difference x bar minus y bar minus the margin of error, okay, MOE, and same thing x bar minus y bar difference mean plus margin of error. Finally, we can print these. So we can give the command print. We can again use this f string. True mean for 1 we have written, so that is your true mu. True mu 1. Again, same thing would be for your second one. True mu 2 would be there, and if you want to see what is the sample mean for the first one that we have calculated, sample 1 mean, we can write sample 1 mean. So sample 1 mean we calculated as mean 1, okay, mean 1, and if I write sample mean of the second one also, so that would be sample 2 mean. So here it would be mean 2. And finally, we will have the confidence interval. So print CI for basically for pool t interval, or you can write for difference of means. So this one would be your CI. So what you can see from here is that your mu1 was 35, mu2 was 30, sample mean came out as 34.5, and for the second sample it came out as 31.5 approximately, and the confidence interval we have obtained is 1.93 to 4.24. So this is for mu1 minus mu2. Okay, so the difference of the population mean, so we are 95% confident that it is going to lie in this interval. So this code basically conducts a 2 sample pool t test to estimate and create a confidence interval for difference between 2 population means. Okay. Now note that here, since we are using .ppf, this percent point function, that is why we have used 1 minus alpha by 2. Rather, in the results in theory part, if you would see, it is alpha by 2. T alpha by 2 n plus m minus 2. Basically, both of them give the same answer because it is the way that this function is defined in your Python, like the library SciPy. So that is why we are writing it 1 minus alpha by 2. So basically, this would tell and find out the t value that corresponds to the right tail probability of 1 minus alpha by 2. So it is the same thing basically. So don't get confused with this PPF function. So now we move on to the next step, that is your Wells T interval. So let me mention that as a comment. So Wells T interval, in this case, how is it different from the previous one, that is the pooled one? Here the variances would also be different. Population means as well as the variance will be different, and in the pooled one the variances are same. That is why we kept it 25. So here we are going to take it as different. So although we have imported these libraries, I can just restart and run all so that it gets updated. Okay, so we don't, since we have already imported the libraries numpy and scipy from scipy.stats, we have imported T, and we can keep it as it is. So np.randomseed, let me ensure this also. So let me just write this. Now we will write the true population parameters. So true population parameters would be true mu1, that would be suppose 35, true mu2, let that be 30, as we have defined earlier also. Now your true sigma underscore sq1, so sigma square, that is first variance, let that be 25, and the other one, let that be 36. Okay, so here we are taking different variances as opposed to the previous one. Now we can also write the sample sizes. So sample sizes, as we have taken earlier also, n40 and m as 30. Okay, so these were the same things that we have defined earlier. Now we are going to generate the sample from normal distribution. Generate a random sample. So data dot sample 1 np dot random dot normal. So here it is, the step is same, with just the difference that here we would have to give the different variances for both the samples. So np dot sqrt, so here again we would write true sigma sq1, and here we would specify the sample size, that is n, and for the second one so here it would be np2, and here it would be sigma 2, and finally m, sample size is m. We would now calculate the means, or you can say the sample statistics. Calculate the sample statistic. We can also directly copy this because it is the same command that we have over here. So mean 1, mean 2 would be same, SD1 and SD2. Yeah, so this basically this entire step would be the same. Okay. Now, if you remember, in Wells T interval, the degrees of freedom for Wells is a bit complicated, and it will have a numerator that was denoted by R. We had some term in the numerator and then in the denominator. So let me just write those things. Calculate the degrees of freedom for Wells T interval. So numerator, let me mention num. So if it is basically sample variance of first one, that is sx square over n plus sy square over n, m, that is its sample size, and whole raised to the power 2. So let us write that SD1. So SD1. So because here we have considered the square root, so it would be raised to the power 2 divided by n plus SD2 divided by m whole raised to the power 2. And similarly, denominator would be, in that case, it is sx square over n whole square divided by n minus 1 plus sy square over m whole square divided by m minus 1. So the denominator in this case would be sd1 sx square divided by n. Again, it would be raised to the power 2, and this whole would be again divided by n minus 1. And similarly, another term would come over here. So it would be sd2 sy square divided by m whole square divided by m minus 1. So the degrees of freedom, that is DOF, in this case would be numerator divided by denominator. So this is basically your R. Now we are ready to set the confidence level. So we can use the previous steps that we have defined, set the confidence level and the critical values and all those things. So the confidence level is again 0.95. Alpha is 1 minus confidence level. Degree of freedom we have already calculated above, because here it is not same as n plus m minus 2, but rather it is defined in this input line 14 over here. And the T critical, again we will use this, it would be DOF, right? That is same. Okay, now let us calculate the margin of error. So the margin of error here, it would be squared. First we will calculate the square of this, squared SD, it would be SD square, SD1 SD square divided by 2, SD1 square divided by, divided by n, plus the second variance sy square, that is SD2 raised to the power 2 divided by m. Now margin of error in this case would be T critical that we have obtained, okay, into P dot sqrt of this squared SD, because it is under root of sx square over n plus sy square over m, right? So you have T critical evaluated at these degrees of freedom, and you are multiplying it with sx square over n plus sy square. So this is the margin of error, and finally you can substitute it for calculating the difference of means or the confidence interval. So if you want, we can just use it from here. Probably we can use both of them, right? So we will write the difference of means. The difference of means would be x bar minus y bar, and confidence interval in this case would be difference of means minus MOE, the same thing. Okay, finally we can print all these and let us see. So let us see what is mean 1. If you see what is mean 1, mean 1 was 34.5, mean 2 was 31.79, mu 1 mu 2, if you remember, it is 35 and 30, right? 35 and 30. Now what do we need? We need the confidence interval. So let us see what is the updated confidence interval. You can see that it goes from minus 0.273 to 5.85, because we have different variances in this case. So the confidence interval also gets modified in the same way. So this is basically your 95% confidence interval, which means that we are 95% confident that the difference of the population mean is going to lie between these two. So the third case for your confidence interval, in case of two problems, it was the paired T interval. So let us see what do we do in this case. If you remember, there we had, since it is a paired sample, so we will have D bar plus minus T alpha by 2 n minus 1 into SD divided by square root of n, right? So we already have the necessary libraries. So let us just write the sample data. So we are just taking this. So data 1, data 1 is the before one, or maybe I can write data B before only I would write. So let this be basically an array. So it would contain, suppose, 45, 50, 48, 55, 42, 47, 53, 52, 49 and 46. Okay, so these are some random values that we have taken. So basically here we are defining these measurements. So data before, so here it has 3, 6, 7, 9, 10 observations. 45, 50, 48, 55, 42, 47, 53, 52, 49, 46. Likewise, I can define what is the data afterwards. So in this case, it can be, suppose, 38, 42, 40, 48, 35, 41, 45, 40, 39, 37. Okay. Now we can calculate the differences. So differences would be np.array. So numpy's array. So basically it is converting the list that we have defined over here into a numpy array. So this numpy and np.array, so we will write data before. It is taking the difference between this and np.array data underscore after. So basically it is doing element wise subtraction of these two arrays, and then it is storing it in this differences array. Okay, now let us see what is the length. Length is, we know that length of these differences, this is going to be 10 only. So let me just see what is n. N is 10. Now we can calculate the sample statistic. So the mean difference, that is d bar, it would be np dot mean of these differences that we have calculated, and std, standard deviation difference, this would be np dot std differences, that is difference that we have calculated, at DDOF, that is the sample variance. Okay, so we are calculating SD, sample standard deviation, over here. Again, we can set the confidence level and other things. So it would be, confidence level is 0.95, alpha is this, and here again we have the same things. So remember that what I told you about the percent point function. So if you in the theory part, if you have alpha by 2, so in code when you are writing in Python, so it would be 1 minus of alpha by 2, because of the way this function is defined in this library. Okay, now if we have to calculate the margin of error, so margin of error would be MOE. Margin of error in this case would be T critical, which is T alpha by 2 n minus 1 into SD. So SD is STD difference that we have obtained. So let me just write STD difference divided by square root of n. So we will write NP dot square root of n. Sorry, it should not be MP, it should be MO. And finally, you can write the confidence interval. Margin of error is there, so your CI would be mean difference, that is D bar, mean difference minus your margin of error, and mean difference plus margin of error. So let us see what is your confidence interval in this case. It is 5.13 to 11.26. And what is the difference between the sample mean? Let me also see what is mean difference. If you want to give a proper print command, that also you can do. It is 8.2. Sample mean difference is 8.2 and the confidence interval comes out as this, from 5.13 to 11.26. So we have basically written this code for determining if there is a significant difference between the paired measurements, and we have constructed a confidence interval to estimate the magnitude of that difference. So this basically completes for your T interval. Whenever you are interested in mu, basically for the difference of means, we have these three tests. First one was the pooled one, pooled interval, where you have variances same in Welch interval, so variances become different, and finally you have paired T interval where the measurements are dependent. Now we are going to look at the confidence interval for ratio of two population variances. Confidence interval for ratio of two population variances. Okay, sigma 1 square over sigma 2 square. So in this case, we need to import numpy. So let us rewrite it. And we also need from scipy dot stats import f. We need f distribution in this case because we are dealing with the ratio of two chi-squares. So if you can recall, we have studied this earlier in sampling distribution and in other places as well. So we need this to calculate the critical f values. Now again we will set the random seed np.random.seed, suppose 123. So basically by setting the random seeds, you ensure that the random samples generated are reproducible. Now we will write the true mu 1, mu 2, sigma 1 square and sigma 2 square. So we can probably take the same values that we have defined earlier. So suppose we are taking this same thing, true population parameters. So let me just use this same setup here. So true mu 1, 35, 30, 25, 36, 40 and 30, right? Now we will generate random samples. You can see that the first few commands are same. Generate random sample. So basically these are the codes when you already have the data and you have the variance and the mean, you know what is happening there. In that case, you can opt for these steps and find out the confidence interval. Okay, so here, so data sample 1, let me write it again. So again it would be from np.random. So we are generating a random sample from normal distribution with mean, true mu 1, variance, that is np.square root we can write. So that would be the standard deviation. That would be true sigma underscore sd1, and finally the sample size would be n. Likewise, you would just copy it. And here it would be true mu 2 sd2 for the second sample, and the second sample the size is for m. Okay, now we are ready to calculate the sample variances. Okay, so true sigma, sq square. Okay, let me just write sq over here, it should not be. Okay, now we will calculate the sample statistic. In this case, it would be the sample variance, right? Because we are dealing with the ratio of two population variance as opposed to the previous codes where we were dealing with the sample means. So here we will write sample variance 1, sample var 1 to find out the variance of the data sample, first one, that is data sample 1, and we would write DDOF as 1 in order to ensure that we are dealing with sample variance. Likewise, we can rewrite it and see that it would be sample variance 2 for the second sample in this. So here we are using np.var function from NumPy library in order to calculate the sample variances. And we know that DDOF is 1. Basically, it specifies the Bessel's correction in order to get the unbiased sample variance, that is 1 over n minus 1 should be in the denominator. N minus 1 should be in the denominator. Now we set the confidence level. So confidence level, we have been taking it as confidence level. Let me just write it. So conf level would be 0.95 and alpha, let that be. So alpha in this case would be 1 minus of conf level. Now we will calculate the critical values. So here in ratio of population variances, we use C and D notations. C is used for first one, so f dot ppf, percent point function. In this case, to calculate the percentile from your f distribution, basically it is the inverse CDF, right? So it would be alpha by 2 in this case, m minus 1, n minus 1, and what will be D? Note that is again the reverse of what you have in your slides, because it is alpha by 2 and 1 minus alpha by 2 are switched. M minus 1, n minus 1. C also, if you can recall from the theory, it is f at 1 minus alpha by 2, m minus 1, n minus 1, or you can say 1 over f alpha by 2, n minus 1, m minus 1, and D is this. So these lines will calculate the critical f values. C, in this case it will calculate for C, and this one will calculate the critical value D for the upper bound of the confidence interval. Okay, now we will use these critical values to construct the confidence interval for ratio of two variances. So let me write that as lower bound. Suppose lower bound would be, because if you recall, it would be C times sample variance 1 divided by sample variance 2, S1 square over S2 square. So a sample underscore var 1 divided by sample underscore var 2. Similarly, upper bound would be D times sample variance 1 and divided by sample variance 2. Okay, so if you want to see the confidence interval for this, we can see what is the lower bound for this, 0.38, and the upper bound over here is 1.55. Okay, so if you want to be, so let me just write few commands for print so that it is easier for you to understand. So sample variance 1 would be your sample underscore var 1. Okay, and the second one would be same thing. We can, for the second sample variance, sample var 2. And now we can also print your confidence interval in this case, confidence interval for ratio of population variance, that is sigma 1 square over sigma 2 square. So here it would be the lower bound, confidence interval would be in this form. So first we will have the lower bound, and then we will have the upper bound. So sample variance was 34.87, 44.0. So the initial one The original one is 25 and 36. So you can see that sample variance is 34 and 44 in this case, and this is basically your confidence interval for ratio of the two population variances. So finally, we move on to the confidence interval for difference of two population parameters, difference of two population proportions. So let us import numpy as np, and from scipy dot stats import norm, because in this case you can recall that we use normal distribution, right, when we are talking about proportion, because binomial can be approximated using the normal distribution. So in this case, let us first see what are the sample sizes. So let the first population size, sample size be 300, n1, and n2 be 400. Let me take p1 hat as 0.6, that is the sample proportion for the first population, and p2 hat basically would be suppose 0.55. Okay, this is the sample proportion corresponding to the second one. Let us take the confidence level as 0.95 and alpha as 1 minus of this confidence level. Now the critical value in this case, Z critical would be norm dot ppf, and here we would write 1 minus alpha by 2, right? So we are using this scipy's module norm function over here. From norm module we are using this function norm dot ppf, which calculates the percent point function, or you can say the inverse CDF for the standard normal distribution with mean 0 and variance this. So basically, in other words, it will tell you the Z value for the given cumulative probability. And Z critical is there. You can also calculate the margin of error now. So margin of error, if you can recall, it would be Z alpha by 2 we write, and under square root of p1 hat 1 minus p1 hat divided by this first sample size plus p2 hat into 1 minus p2 hat divided by the second one. Okay, so let me just mention that Z critical into np dot sqrt, it would be p1 hat into 1 minus p1 underscore hat. This whole would be divided by n1 plus p2 underscore hat into 1 minus p2 underscore hat, p2 hat, okay, divided by, so here should be multiple p2 into 1 p2 hat into 1 minus p2 hat whole divided by the second sample size. Now you will have the difference of proportions. Different prop would be p1 hat minus p2 hat, and your CI, that is the confidence interval, would be difference proportion minus your margin of error, and difference proportion plus margin of error. So let us see what is the first p1 hat. P1 hat, P2 hat we already have, right, 0.6 and 0.55, and then we write the confidence interval. So let us see what is the confidence interval in this case. It is from minus 0.02 to 0.12. So this basically tells you that we are 95% confident that the difference of the two population proportions would fall between these two endpoints. So this is how you can calculate the confidence interval for a given data set and for the given values at certain confidence level. So obviously you can change the confidence level according to your problem, and these things, these steps you can keep on defining and you will get the answer.